Hello everyone. Welcome back to my course Fundamentals of Thermodynamics, Essential Knowledge for Engineers. In this video, we will talk about gas laws and the ideal gas, understanding pressure, volume, and temperature relationships. Also, I will be thankful if you give me feedback about this course to make it better and more useful for you. Please write down your thoughts in the comment section or reach out to me via the email provided in my profile. Boyle's Law. Air is a gas, and like all gases, it has certain properties that we can measure and observe. These include the gas pressure, P, temperature, T, mass m, and the volume, V, that contains the gas. Careful scientific observations have shown that these properties are not independent of each other. Instead, they are connected in such a way that together they define what is called the state of the gas. In the mid-1600s, the English scientist Robert Boyle carried out experiments to understand the relationship between pressure and volume. He studied confined gas at a constant temperature and discovered that when the volume decreases, the pressure increases in such a way that their product, pressure multiplied by volume, remains nearly constant. For an ideal gas, this relationship holds perfectly. This became known as Boyle's Law, named in his honor, and it forms one of the fundamental building blocks of thermodynamics. A simple everyday example of this law is seen in a syringe. When you push the plunger, you decrease the volume of the air trapped inside, and the pressure rises. More generally, scientists learned that we can investigate gas behavior by holding any two of the four main properties, pressure, volume, temperature, and mass, constant, and then studying how the other two properties change with each other. To demonstrate this idea, imagine a schematic gas lab. In this lab, a gas is confined inside a blue container. The yellow space inside represents the gas volume, which is controlled by the position of a red piston at the top of the container. The piston can move up or down using a screw mechanism, allowing the volume of the gas to be increased or decreased. The amount of gas is represented by the number of small black molecules inside the container. By using a pump on the side, you can inject more molecules or withdraw some, which changes the number of moles of gas. At the bottom of the container, two probes are inserted. One measures pressure and the other measures temperature. The pressure of the gas can be changed by adding or removing green weights on top of the piston, while the temperature can be changed by heating the container with a torch. This simplified laboratory setup makes it easier to visualize how gases behave. For example, when you increase the weights on the piston, you are applying more pressure, so the piston moves downward and the volume decreases, an illustration of Boyle's law. Or, if you heat the container with the torch, the temperature rises and the gas expands, pushing the piston upward, which demonstrates Charles' law. In this way, the gas lab shows how each property is linked with the others, reinforcing the idea that the state of a gas is determined by the combination of pressure, temperature, volume, and mass. Charles and Gay-Lussac's law. The relationship between temperature and volume, when the number of moles and the pressure are kept constant, is known as Charles and Gay-Lussac's law. This law is named in honor of the two French scientists who first investigated it. Jacques Charles carried out the original experiments, and Joseph Gay-Lussac later verified and extended his findings. Together, they observed that when the pressure of a gas is held constant, its volume is directly proportional to its temperature. In other words, if the temperature increases, the volume also increases. If the temperature decreases, the volume shrinks. This principle can be seen in everyday life. For example, think about a hot air balloon. As the air inside the balloon is heated, the gas molecules move faster and spread out, causing the balloon to expand. Because the pressure inside and outside the balloon stays balanced, the increase in temperature leads directly to an increase in volume. Similarly, on a cold day, the volume of air inside a football decreases slightly, making the ball feel deflated, an effect of this same law. From a scientific perspective, we can study this relationship by fixing two of the four main gas properties: pressure, temperature, volume, and number of moles, and then varying one of the others while observing the response. To demonstrate this concept, once again imagine a schematic gas lab. In this setup, a theoretical gas is confined inside a blue container. The yellow region inside represents the volume of the gas, which is controlled by the position of a red piston at the top. By turning a screw attached to the piston, the volume can be increased or decreased. The number of gas molecules, which represents the number of moles, is shown as small black particles inside the container. These can be added or removed using a pump on the side, allowing the total amount of gas to change. Two probes extend into the container from below. One measures the pressure of the gas, and the other measures its temperature. The pressure can be adjusted by placing green weights on top of the piston, while the temperature can be altered by heating the container with a torch beneath it. This simplified laboratory model helps us visualize how gases respond to changes in conditions. For Charles and Gay-Lussac's law, if the weights on the piston are left unchanged, so the pressure stays constant, and we use the torch to heat the container, the temperature rises. As a result, the piston is pushed upward and the gas volume increases. If the container cools instead, the piston moves downward and the volume decreases. This experiment shows clearly how gas volume depends directly on temperature when pressure and the number of moles remain constant. The combined gas law. The combined gas law is a way to relate pressure, volume, and temperature for a fixed amount of gas. It essentially combines Boyle's law and Charles' law into a single equation. Boyle's law showed that at constant temperature, the pressure of a gas is inversely proportional to its volume. Charles' law demonstrated that at constant pressure, the volume of a gas is directly proportional to its temperature. The combined gas law allows us to consider situations where both pressure and temperature are changing simultaneously, while the amount of gas remains constant. Mathematically, the combined gas law can be written as the pressure multiplied by the volume divided by the temperature is equal to a constant. Or comparing two different states of the same gas. The initial pressure multiplied by the initial volume divided by the initial temperature is equal to the final pressure multiplied by the final volume divided by the final temperature. Here, the initial pressure, initial volume, and initial temperature are the starting conditions of the gas, and the final pressure, final volume, and final temperature are the values after a change occurs. The temperature must always be measured on an absolute scale in Kelvin to ensure the relationship is valid. In practical terms, the combined gas law helps us predict how a gas will behave when it experiences multiple changes at once. For example, imagine a sealed balloon outdoors. On a hot day, the air inside heats up, causing the temperature to rise. If the balloon is squeezed slightly, reducing its volume, the pressure inside increases. Using the combined gas law, we can calculate exactly how the pressure, volume, or temperature will change relative to each other. Another example is in scuba diving. As a diver descends, the water pressure increases, compressing the air in their tank and changing its volume. If the diver also experiences temperature changes in the water, the combined gas law allows precise calculations of the tank's internal conditions, which is crucial for safety. The combined gas law is an important tool in thermodynamics because it shows that pressure, volume, and temperature are interconnected. Any change in one property affects the others, and understanding this relationship allows scientists and engineers to predict the behavior of gases in real-world applications, from balloons and tires to industrial processes and aerospace engineering. Ideal gas. As we said before, air is a gas, and like all gases, it possesses several observable properties. These include the pressure of the gas, denoted as P, its temperature, T, its mass m, and the volume V that contains it. Through careful scientific observation, we have determined that these properties are not independent. They are interconnected, and the combination of their values determines the overall state of the gas. If we fix any two of these properties, we can explore the relationship between the remaining two. For instance, if the pressure and temperature are held constant, the volume of the gas varies directly with the mass of the gas. In other words, increasing the amount of gas increases the volume proportionally, and vice versa. This relationship allows us to define another important property called gas density, R, which is the ratio of the gas's mass to its volume. Similarly, if the mass and temperature are held constant, the product of pressure and volume remains nearly constant for a real gas. For an ideal gas, this product is exactly constant. This relationship is known as Boyle's law. On the other hand, if the mass and pressure are held constant, the volume of an ideal gas is directly proportional to its temperature. This relationship is referred to as Charles and Gay-Lussac's law. These individual gas laws can be combined into a single equation of state, which summarizes the relationship between pressure, volume, temperature, and the amount of gas. This equation is commonly written as pressure multiplied by volume divided by temperature equals number of moles multiplied by the universal gas constant. In this equation, N is the number of moles of gas and R is the universal gas constant. By performing a little algebra, we can rewrite this equation in a more familiar form. Pressure multiplied by volume equals number of moles multiplied by the universal gas constant multiplied by temperature. This equation can be represented graphically in 3 dimensions, where the intersection of any two lines corresponds to a unique state of the gas. In aerodynamics, a slightly modified form of this equation is used specifically for air. By dividing both sides of the general equation by the mass of the gas, the volume becomes the specific volume, which is the inverse of the gas density. A new gas constant, also denoted R, is defined as the universal gas constant divided by the mass per mole of the gas. Unlike the universal gas constant, which is the same for all gases, this new constant depends on the type of gas. For air, this constant has a value of 0.286 kilojoules per kilogram per degree Kelvin. The equation of state for air can therefore be written either in terms of specific volume or in terms of air density as follows. Pressure multiplied by specific volume equals the gas constant multiplied by temperature, or pressure equals gas density multiplied by the gas constant multiplied by temperature. It is important to remember that this equation applies only to an ideal gas or a real gas that behaves similarly to an ideal gas. In reality, there are many different forms of the equation of state for different gases. Additionally, the temperature used in these equations must always be an absolute temperature, measured from absolute zero. In the metric system, this is expressed in degrees Kelvin, not Celsius, and in the English system, it is expressed in degrees Rankine, not Fahrenheit. Okay guys, to better understand what we have learned today and to visualize a real-life example, let's experiment a little with the 4 primary properties of gas in our digital gas laboratory. Welcome to the animated gas lab. Here, we get to explore the fascinating world of gases and their properties. Gases have characteristics like pressure, temperature, mass, and volume, the amount of space they occupy. Scientists have discovered that all these properties are connected, and together they define the state of the gas. In this lab, you can freeze any 2 of these properties and then observe how the other 2 change. It's a hands-on way to understand the relationships between pressure, volume, temperature, and mass. Imagine a theoretical gas trapped inside a blue jar. The gas volume is shown in yellow and depends on the position of a red piston. You can change the volume by moving the piston up or down using the red screw on top. The mass of the gas is represented by the little black molecules inside the jar. You can increase or decrease the mass by adding or removing molecules with the pump on the left. To monitor the gas, there are 2 probes at the bottom of the jar that measure pressure and temperature. You can adjust the pressure by placing green weights on top of the piston or removing them. The temperature can be changed by using the torch at the bottom of the jar. This lab gives you a chance to see gas behavior in action, experiment safely, and really understand how pressure, volume, temperature, and mass are all connected. Let's start. First, we will freeze mass and volume and see effect of changing pressure on temperature. If mass and volume are held constant, the gas cannot gain or lose molecules, and the space it occupies does not change. In the animated gas lab, the volume is fixed because the red piston cannot move, and the mass of the gas is fixed because no molecules are added or removed. When you change the pressure, this is done by adding or removing green weights from the top of the red piston. Adding weights increases the downward force on the gas, raising the pressure. Removing weights decreases the downward force, lowering the pressure. Since the volume is fixed and the gas cannot escape, the only way the gas responds to a change in pressure is by changing its temperature. Increasing the pressure forces the gas molecules to move faster, which increases their kinetic energy, thereby increasing the temperature. Decreasing the pressure slows the molecules down, lowering the temperature. So in summary, mass fixed, volume fixed. Add weights, pressure increases, temperature increases. Mass fixed, volume fixed, remove weights, pressure decreases, temperature decreases. This demonstrates Gay-Lussac's law, where the pressure of a gas at constant volume is directly proportional to its absolute temperature. Now we will freeze mass and volume again, but see effect of changing temperature on pressure. If mass and volume are held constant, the gas cannot gain or lose molecules, and the space it occupies does not change. In the lab, the volume is fixed because the red piston cannot move, and the mass of the gas is fixed because no molecules are added or removed. Now, when we change the temperature, we are affecting the average kinetic energy of the gas molecules. Heating the gas using the torch at the bottom of the jar makes the molecules move faster, which causes them to collide with the walls of the container more forcefully and more frequently. This increases the pressure inside the jar. Cooling the gas slows the molecules down, reducing the frequency and force of collisions, which decreases the pressure. In the animated lab, the pressure change is observed by the force on the red piston. Since the piston cannot move, volume is fixed. All changes in the gas behavior show up as changes in pressure. So, in summary, mass fixed, volume fixed, increased temperature, pressure increases. Mass fixed, volume fixed, decreased temperature, pressure decreases. This again demonstrates Gay-Lussac's law, which states that at constant volume, the pressure of a gas is directly proportional to its absolute temperature. Now let's freeze mass and pressure and observe the effect of changing volume on temperature. In the animated gas lab, the volume is changed by moving the red piston using the red screw, while the pressure is maintained by the green weights on top of the piston. This experiment must be performed very slowly and carefully to keep the pressure constant, and the blue jar would need to be heavily insulated to prevent heat loss or gain from the surroundings. As the volume increases, the gas molecules have more space to move, which lowers the frequency of collisions and reduces the kinetic energy per unit volume. This causes the temperature to decrease. Conversely, decreasing the volume forces the molecules closer together, increasing the collision rate and kinetic energy, which raises the temperature. This behavior illustrates Charles and Gay-Lussac's law, where the volume of a gas at constant pressure is directly proportional to its absolute temperature. Summary: mass fixed, pressure fixed, increase volume, temperature decreases. Mass fixed, pressure fixed, decrease volume, temperature increases. On the animation, it's shown a little incorrect, as it shows that when you increase volume, the temperature increases. But it should be vice versa. When you increase volume, the temperature should decrease. So don't mind it. Now let's freeze mass and pressure and observe the effect of changing temperature on volume. In the animated gas lab, the temperature is changed by adding heat from the burner, while the mass and pressure remain constant. As the gas is heated, the molecules move faster, increasing their kinetic energy. Because the pressure is fixed, the only way for the gas to accommodate the increased energy is to expand, which increases the volume. Conversely, if the gas is cooled, the molecules slow down and the volume decreases. This experiment demonstrates Charles and Gay-Lussac's law, where the volume of a gas at constant pressure is directly proportional to its absolute temperature. Summary: mass fixed, pressure fixed, increased temperature, volume increases. Mass fixed, pressure fixed, decreased temperature, volume decreases. Now let's freeze mass and temperature and observe the effect of changing volume on pressure. In the animated gas lab, the volume is changed by adjusting the position of the piston using the red screw, while the mass and temperature remain constant. As the volume of the gas decreases, the molecules are compressed into a smaller space, which increases the pressure. Conversely, increasing the volume gives the molecules more space, which reduces the pressure. This experiment demonstrates Boyle's law, where the pressure of a gas at constant temperature is inversely proportional to its volume. Summary: mass fixed, temperature fixed, decrease volume, pressure increases. Mass fixed, temperature fixed, increase volume, pressure decreases. Now let's freeze mass and temperature again and observe the effect of changing pressure on volume. In the animated gas lab, the pressure is changed by adding or removing green weights from the top of the red piston, while the mass and temperature remain constant. As the pressure on the gas increases, the molecules are compressed into a smaller space, which reduces the volume. Conversely, decreasing the pressure allows the gas to expand, which increases the volume. This experiment also demonstrates Boyle's law, where the volume of a gas at constant temperature is inversely proportional to its pressure. Summary: mass fixed, temperature fixed, increase pressure, volume decreases. Mass fixed, temperature fixed, decrease pressure, volume increases. Now let's freeze volume and pressure and observe the effect of changing mass on temperature. In the animated gas lab, the mass of the gas is changed by injecting molecules using the pump on the left, while the volume and pressure are held constant. As the mass increases, the density of the gas, mass divided by volume, also increases, and this affects the gas's temperature. Decreasing the mass lowers the density and changes the temperature accordingly. This type of experiment would be very difficult to perform in reality, because maintaining both constant pressure and volume while changing the mass is extremely challenging. Summary: volume fixed, pressure fixed, increase mass, density increases, temperature changes. Volume fixed, pressure fixed, decrease mass, density decreases, temperature changes. Now let's freeze volume and temperature and observe the effect of changing mass on pressure. In the animated gas lab, the mass of the gas is changed by injecting molecules using the pump on the left. Since the volume is fixed by the position of the red piston and the temperature is held constant, adding more mass increases the density of the gas, mass divided by volume. As a result, the pressure of the gas also increases. Removing molecules decreases the density, lowering the pressure. Summary: volume fixed, temperature fixed, increase mass, density increases, pressure increases. Volume fixed, temperature fixed, decrease mass, density decreases, pressure decreases. Now at last, let's freeze pressure and temperature and observe the effect of changing mass on volume. In the animated gas lab, the mass of the gas is changed by injecting molecules using the pump on the left. Since the pressure is held constant by the green weights on the piston, and the temperature is maintained using the heating system, the volume of the gas changes proportionally with the mass. This keeps the density, mass divided by volume, constant, because both pressure and temperature are fixed. Summary: pressure fixed, temperature fixed, increase mass, volume increases, density constant. Pressure fixed, temperature fixed, decrease mass, volume decreases, density constant. Okay guys, now let's have a little quiz. The quiz consists of 5 questions. I'll give you 10 seconds for each one, and then I'll show you the correct answer. Let's start with the first question. Question 1. Boyle's law describes the relationship between which two properties of a gas when temperature is held constant? The correct answer is pressure and volume. Question 2. If a gas is kept at constant pressure What happens to its volume when the temperature increases? The correct answer is it increases. Question 3. The combined gas law combines which two gas laws to account for changes in pressure, volume, and temperature simultaneously? The correct answer is Boyle's law and Charles' law. Question 4. What happens to the pressure of a gas if its volume is decreased while the mass and temperature remain constant? The correct answer is the pressure increases. Question 5. Which of the following is true about gas density in the context of the ideal gas law? The correct answer is density is the ratio of gas mass to its volume. Unlock the world of aerospace engineering with my other expertly designed courses. In Aerospace Engineering, Basics of Aviation Engines, you'll explore the different types of aerospace engines and how they perform, giving you a strong foundation in the propulsion systems that power modern aircraft. Then, take your knowledge to new heights with Aerospace Engineering, Aerodynamics and Structures, where you'll dive into the design and performance of aerospace structures and their aerodynamic behavior. Finally, expand your expertise with Aerospace Engineering, Avionics and Aerospace Systems, where you'll learn about the critical electronic systems that control and monitor modern aircraft, bridging the gap between engines, structures, and flight systems. Whether you're a student, aspiring engineer, or aviation enthusiast, these courses will equip you with essential knowledge to understand and contribute to the future of aviation. Join hundreds of learners and start building your aerospace journey today. Thank you guys for watching this video. If you have any questions about this lesson, feel free to ask me in the comment section. I will answer as soon as possible. We can continue to the next lesson and learn about speed of sound, Mach number, and flight regimes. See you in the next video. Bye.